Welcome to DAR Tutors for Online and Home Tuition. In this video, we will delve into the application of Le Châtelier's principle to analyze and predict changes in chemical equilibria. This is a critical topic for your IB Chemistry higher level curriculum. Our focus will be on understanding how to interpret concentration and rate graphs for systems in equilibrium that have been subjected to a disturbance. You will learn how to explain the effects of changing concentration and temperature on an equilibrium, both qualitatively and quantitatively. Furthermore, we will examine the impact of pressure on gaseous equilibria, a key aspect often tested at the HL level. By the end of this session, you will be proficient in using Le Châtelier's principle to solve complex IB-style problems. Let's begin by reviewing the fundamental principle we will be applying. Le Châtelier's principle states that if a dynamic equilibrium is disturbed by changing the conditions, the position of equilibrium moves to counteract the change. This means the system will shift in a way that minimizes the effect of the disturbance you've imposed. The equilibrium constant, K, is a measure of the position of equilibrium. For any given reaction, K remains constant unless the temperature is changed. This is a critical point. Changes in concentration or pressure will cause a shift in the equilibrium position, but they will not change the numerical value of K. Only a change in temperature can do that. Now, let's look at how we can visualize these changes using graphs. We will use the Haber process as our primary example. This is the synthesis of ammonia from its elements. The balanced chemical equation is N2 gas plus 3H2 gas in equilibrium with 2 NH3 gas. Suppose we have this system at equilibrium and then increase the concentration of one of the reactants, nitrogen gas, at a constant volume and temperature. First, let's consider the concentration graph. Initially, at time 0, the concentrations of N2, H2, and NH3 are constant, indicating the system is at equilibrium. At time 1, we add nitrogen. This causes a sudden, instantaneous jump in the concentration of N2. Notice that the concentrations of the other species, H2 and NH3, do not change at this exact moment because the volume is constant, and the molecules haven't had time to react yet. The increased N2 concentration disturbs the equilibrium. According to Le Châtelier's principle, the system will shift to the right to consume the excess N2. Consequently, the concentration of N2 will decrease from its peak. The concentration of H2 will also decrease, and the concentration of the product, NH3, will increase. They will all level off at new, stable concentrations as a new equilibrium is established. Crucially, compare the final concentrations to the initial ones. The final N2 is higher than the initial N2 because we added it. The final H2 is lower and the final NH3 is higher. This confirms a shift to the right, favoring the products. Now let's examine the effect of adding nitrogen on the reaction rates. This provides a more microscopic explanation for the concentration changes we just saw. We'll use a graph that plots reaction rate against time. Before to 1, show a single constant line representing both forward rate and backward rate. Label it equilibrium rate. At the initial equilibrium, the forward rate of reaction is equal to the backward rate, so we see a single line representing both. At time to 1, when we add nitrogen, the concentration of N2 increases. Since N2 is a reactant in the forward reaction, this immediately increases the rate of the forward reaction. At that exact moment, the concentration of the products, NH3, has not changed, so the rate of the backward reaction remains constant. This creates an imbalance where the forward rate is much higher than the backward rate. Because the forward reaction is now faster, it starts to consume N2 and H2 and produce NH3. The concentration of reactants decreases, and the concentration of products increases. As the concentrations of N2 and H2 decrease, the forward rate begins to slow down. As the concentration of NH3 increases, the backward rate begins to speed up. This continues until the forward and backward rates become equal again, establishing a new equilibrium. Notice that the new equilibrium rate is higher than the original equilibrium rate. This is because all three concentrations are now higher than their initial values, leading to a faster rate of reaction in both directions. This rate graph confirms the shift to the right we observed in the concentration graph. Now let's consider the opposite scenario, removing a product from the equilibrium mixture. This is a common industrial strategy to increase the yield of a desired product, for instance, by condensing ammonia out of the mixture in the Haber process. We will once again consider the Haber process, but this time, the disturbance is the removal of ammonia. First, the concentration graph. We start at an initial equilibrium with constant concentrations of reactants and products. At time to 1, we remove some ammonia. This causes a sudden, instantaneous drop in the concentration of NH3. The concentrations of N2 and H2 are unaffected at this exact moment. This drop in NH3 disturbs the equilibrium. According to Le Châtelier's principle, the system will shift to the right to produce more NH3 and counteract the loss. As the reaction shifts right, the concentration of N2 and H2 will decrease, and the concentration of NH3 will increase from its minimum point. A new equilibrium is reached when the concentrations become constant again. Comparing the final concentrations to the initial ones, we see that the final N2 and H2 are lower, and the final NH3, although having recovered, is still lower than its original value. This confirms a shift to the right. Let's now consider the rate graph for the removal of ammonia, which again explains the mechanics of the shift. We'll use our rate versus time graph. At initial equilibrium, the forward and backward rates are equal. At time t1, we remove ammonia. This causes an instantaneous drop in the concentration of NH3. Since NH3 is the reactant in the backward reaction, this causes a sharp, instantaneous decrease in the backward rate. At this moment, the concentration of reactants has not changed, so the forward rate is unaffected. This creates an imbalance where the forward rate is now greater than the backward rate. Because the forward reaction is faster, the concentrations of N2 and H2 decrease, while the concentration of NH3 increases back towards equilibrium. As this happens, the forward rate starts to slow down due to decreasing reactant concentrations, and the backward rate starts to speed up due to increasing product concentration. This continues until the rates become equal again, establishing a new equilibrium. Crucially, the new equilibrium rate is lower than the original equilibrium rate. This is because at the new equilibrium, the concentrations of all species are lower than they were initially, leading to a slower overall reaction rate in both directions. This confirms the shift to the right, but at a reduced speed. We've now seen how to interpret these graphs to understand equilibrium shifts. Let's practice with a worked example. Here's a worked example that requires you to analyze a graph and connect it to Le Châtelier's principle. Consider the following reaction. X aqueous plus Y gas in equilibrium with Z gas. The standard enthalpy change of reaction is negative, which means the forward reaction is exothermic. The graph shows the number of moles of each gas over time. Let's analyze what happened at time t. The amount of Z gas, a product, increased instantaneously and then continued to increase gradually. The amount of Y gas, a reactant, decreased instantaneously and then continued to decrease gradually. The amount of X aqueous, the other reactant, shows only a gradual decrease. The fact that Z and Y showed an instantaneous change at time t is key. This indicates a disturbance that caused a sudden change in concentration or pressure. The gradual changes that follow represent the system shifting to a new equilibrium. Notice that the shift is to the right, towards the products, because the amount of Z is increasing and the amount of Y is decreasing. So we are looking for a disturbance at time t that causes an instantaneous decrease in Y and instantaneous increase in Z, followed by a shift to the right. Let's evaluate the given options. Option 1, an increase in pressure. The number of moles of gaseous reactants is 1 from Y, and the number of moles of gaseous products is also 1 from Z. Since they are equal, an increase in pressure would have no effect on the position of equilibrium. This is incorrect. Option 2, addition of water. This would dilute the aqueous solution, causing a decrease in the concentration of X. According to Le Châtelier's principle, the system would shift to the left to produce more X. This is the opposite of what the graph shows, so it's incorrect. Option 3, an increase in temperature. The forward reaction is exothermic, so the reverse reaction is endothermic. To counteract an increase in temperature, the equilibrium would shift to the left to absorb the added heat. This would decrease the amount of Z and increase Y, which is the opposite of the graph. So this is also incorrect. Since none of the given options correctly explain the observed changes, the answer must be D. At the 10-minute mark, a call to action is added for DAR tutors. Now let's delve into the effect of changing pressure on gaseous equilibria. It's important to understand the conditions required for pressure to have an effect. A change in pressure will only shift the position of equilibrium if the reaction involves gases, and if the total number of moles of gaseous reactants is different from the total number of moles of gaseous products. According to Le Chatelier's principle, if you increase pressure, the system will shift to the side with fewer moles of gas to relieve that pressure. If you decrease pressure, it will shift to the side with more moles of gas. Remember, the equilibrium constant K is not affected by pressure changes. Let's apply this to a few examples. Consider the reaction where N2O4 gas is in equilibrium with 2 moles of NO2 gas. Here we have 1 mole of gaseous reactant and 2 moles of gaseous products. If we increase pressure, the equilibrium will shift to the side with fewer moles of gas, which is the reactant side. So, the equilibrium shifts to the left, favoring N2O4. If we decrease pressure, the equilibrium shifts to the right, towards the side with more moles of gas, favoring NO2. Next example. H2 gas plus I2 gas in equilibrium with 2 moles of HI gas. In this case, we have a total of 2 moles of gaseous reactants and 2 moles of gaseous products. Since the number of moles is the same on both sides, a change in pressure will have no effect on the position of equilibrium. The equilibrium concentrations will remain the same. Last example. H4 gas plus H2O gas in equilibrium with CO gas plus 3H2 gas. Here we have a total of 2 moles of gaseous reactants and 4 moles of gaseous products. The product side has more moles of gas. If we increase pressure, the equilibrium will shift to the left to reduce the pressure. If we decrease pressure, the equilibrium will shift to the right to produce more moles of gas. Now let's analyze the effect of temperature on chemical equilibria. This is the only factor that can change the value of the equilibrium constant, K. The direction of the shift depends on whether the reaction is exothermic or endothermic. A reaction is exothermic if the standard enthalpy change is negative, meaning it releases heat. A reaction is endothermic if the standard enthalpy change is positive, meaning it absorbs heat. We can think of heat as a reactant in an endothermic reaction and a product in an exothermic reaction. This makes the application of Le Chatelier's principle straightforward. If the forward reaction is exothermic, we can write heat as a product. If the temperature is increased, we are adding more heat. To counteract this, the equilibrium will shift to the left, absorbing the excess heat. This means the value of K will decrease. Conversely, if the forward reaction is endothermic, we can write heat as a reactant. If the temperature is increased, the equilibrium will shift to the right to consume the added heat. In this case, the value of K will increase. Remember the key takeaway. For an exothermic reaction, a higher temperature gives a smaller K. For an endothermic reaction, a higher temperature gives a larger K. Let's work through an example. Consider the synthesis of methanol from carbon monoxide and hydrogen gas. The standard enthalpy change is negative, so this is an exothermic reaction. If we increase the temperature, the equilibrium will shift to the left, favoring the reactants to absorb the added heat. As a result, the value of the equilibrium constant K will decrease. There are a few other important factors to consider, particularly in IB chemistry HL. First, the effect of catalysts. A catalyst works by lowering the activation energy for both the forward and backward reactions equally. It speeds up the attainment of equilibrium but has no effect on the position of equilibrium or the value of K. So, a catalyst is useful for making a reaction reach equilibrium quickly, but it won't give you a higher yield of product. Second, the effect of adding an inert gas, like neon or argon. If the volume of the reaction container is kept constant, adding an inert gas increases the total pressure. However, it does not change the partial pressures of any of the reactants or products. Since the equilibrium is determined by partial pressures, there is no shift. If the pressure is kept constant by increasing the volume, then the partial pressures of the reactants and products would decrease, causing a shift towards the side with more moles of gas. Third, we must carefully consider reactions with pure solids or liquids. For example, in the decomposition of calcium carbonate, the equilibrium expression for Kp only involves the partial pressure of the gaseous product, carbon dioxide. The pure solid KCO3 and the pure solid CaO are not included in the expression, and therefore their amounts do not affect the equilibrium position. You can add or remove solid KCO3 or CaO without shifting the equilibrium, as long as some of the solid is present. Let's work through one more complex example, often seen in IBHL exams, to solidify our understanding. Consider the following gas phase reaction: the interconversion of oxygen and ozone, with a positive enthalpy change. We need to predict how the position of equilibrium and the value of the equilibrium constant K are affected by an increase in temperature and an increase in pressure. First, the effect of an increased temperature. The enthalpy change is positive, so the forward reaction is endothermic. To counteract an increase in temperature, the equilibrium will shift to the right to absorb the added heat. This means more ozone will be produced. Because the forward reaction is favored, the equilibrium constant K will increase. So a higher temperature yields more ozone and a larger equilibrium constant for this reaction. Next, the effect of an increased pressure. We must compare the moles of gaseous reactants and products. On the reactant side, we have 3 moles of oxygen. On the product side, we have 2 moles of ozone. Since there are fewer moles of gaseous products, an increase in pressure will shift the equilibrium to the right, favoring the production of ozone. Note that pressure changes do not affect the value of K, so K remains unchanged. In this specific case, both increasing the temperature and increasing the pressure will shift the equilibrium to the right, leading to a higher yield of ozone. However, they affect the equilibrium constant in different ways, so it's essential to distinguish between a shift in position and a change in K. Now it's time to test your understanding with some IB-style practice questions. I will give you the question and a few moments to think about it, and then we will go through the full solution. Question 1. Consider the reaction N2-G plus 3H2G equal to H3G at equilibrium. The pressure is increased at a constant temperature. Which of the following describes the change in equilibrium? Pause the video here and take a moment to formulate your answer. Solution. First, identify the number of moles of gas on each side. Reactants have 1 plus 3, which is 4 moles. Products have 2 moles. The product side has fewer moles of gas. An increase in pressure will cause the equilibrium to shift to the side with fewer moles of gas to reduce the pressure. Therefore, the equilibrium shifts to the right, favoring the formation of ammonia. Question 2. For the reaction 3O2G equals 2O3G, with a positive enthalpy change, what happens to the equilibrium constant K when the temperature is increased? Pause the video and think about this. Solution. The enthalpy change is positive, indicating an endothermic reaction. We can write heat as a reactant. Heat plus 3O2 equals 2O3. An increase in temperature is like adding more heat. According to Le Châtelier's principle, the equilibrium will shift to the right to consume the added heat. A shift to the right means the products are favored, which results in an increase in the value of K. Let's continue with 3 more practice questions. Question 3. Consider the reaction H2G plus I2G equals 2HIG at equilibrium. What is the effect of increasing the pressure at constant temperature? Take a moment to decide your answer. Solution. Let's count the moles of gas. Reactants have 1 plus 1, which is 2 moles. Products have 2 moles. Since the number of moles of gaseous reactants is equal to the number of moles of gaseous products, a change in pressure will have no effect on the position of equilibrium. The concentrations of H2, I2, and HI will not change. Question 4. In the reaction CH4G plus H2OG equals COG plus 3H2G, what happens to the equilibrium position if the volume of the container is decreased at constant temperature? Think this one through. Solution. Decreasing the volume of a container for a gaseous mixture is equivalent to increasing the pressure. We can therefore analyze this as an increase in pressure. The reactants have 1 plus 1, which is 2 moles of gas. The products have 1 plus 3, which is 4 moles of gas. The reactant side has fewer moles of gas. An increase in pressure will shift the equilibrium to the left, favoring the reactants, to reduce the overall number of gas molecules. Question 5. For the reaction 2NO2G equals 2NO(G) plus O2G. How does increasing the temperature affect the equilibrium position if the reaction is exothermic? Consider the type of reaction and the change. Solution. We are told the reaction is exothermic. This means heat is a product. We can write 2NO2G equals 2NOG plus O2G plus heat. See, an increase in temperature is like adding more heat to the product's side. Answer: the equilibrium shifts to the left. Let's quickly recap what we've covered today. We began by learning to interpret concentration and rate graphs. We saw how instantaneous changes indicate the application of a disturbance, and the gradual changes that follow show the system restoring equilibrium. We analyzed the effects of changing concentration. Adding a reactant or removing a product shifts the equilibrium to the right. Removing a reactant or adding a product shifts it to the left. We then discussed the effect of pressure on gaseous systems. Increasing pressure shifts to the side with fewer moles of gas, while decreasing pressure shifts to the side with more. No effect occurs if the moles of gas are equal on both sides. Finally, we covered the effect of temperature. An increase in temperature shifts endothermic reactions to the right and exothermic reactions to the left, changing the value of the equilibrium constant, K. Mastering these concepts is crucial for success in IB Chemistry HL. Keep practicing the worked examples and questions to build your analytical skills.